any further questions, so we can all thank Narayan.
Thank you.
And then we can move on to the next talk. Okay, so our next talk is by Federico Zerbini, who's going to give us an overview of elliptic polylogarithms and superstring amplitudes.
Okay, hello. Can you see me? Can you hear me?
Yes, we can see the slides and we can hear you. Okay,
great. So thanks a lot for inviting me to speak to this conference. It's really the third Elliptics conference that I'm attending, so I think I know a lot of people out there, and so hi to everyone I know. And so I was asked to give a review talk on some mathematical aspects of superstring amplitudes, in particular beyond genus 0. And this is not so easy because there are a lot of things to say. So I've decided to focus on elliptic polylogarithms and to give a mathematical introduction to some aspects of elliptic polylogarithms, which I believe are the right aspects to look at if you want to generalize all this to higher genus. And in the very last slide, maybe I will comment a little bit about how one could think of going beyond elliptic polylogarithms from the mathematical viewpoint. Okay, so let me start. So this is the plan of the talk. I'm planning of spending maybe 10 minutes on the classical polylogarithms and the genus 0 amplitudes, because this will motivate the rest of the talk. Yeah. And then I will go to some, let's say, hardcore mathematical concept that I will try to make as easy and accessible as I can in order to justify how people define elliptic polylogarithms. And then I will mention what's the state of the art, or some highlights on the state of the art in genus 1 amplitudes, and what's to do and what's not to do in genus 1 and beyond. Good. So let's start with genus 0. Everyone knows about multiple polylogarithms, I guess. They are sometimes presented as Goncharov polylogarithms when they are presented with this definition. So I wanted to be quite precise here, so let me mention a couple of things. So we have a formal alphabet with 2 letters, and we form words in non-commutative letters. And then I want to cut out of the complex plane 2 lines, which are the branch cuts, which you can pick, for instance, going straight from 0 to I infinity and from 1 to I infinity, so that the logarithm function is well defined on U, which is a complex plane without these 2 lines. Why? Because the fundamental group of U is trivial, so it's simply connected. And well, of course, I need to choose a branch of the logarithm, but then I define multiple polylogarithms just in this way. So if you have a string of x zeros, you have the log, powers of the log. And then for any other words, you just define it recursively. So you get iterated integrals. And well, these are well defined because in principle I should specify what's the path, but it turns out that it doesn't matter what's the path, because these integrals are homotopy invariant and our U is simply connected. So you can take any path you want inside U. And well, this gives an analytic continuation to the usual, usually defined multiple polylogarithms, which are defined as multiple sums. It's here. Because, I mean, they're only defined in a radius 1 circle. And you can extend these functions even further to the whole sphere without 0, 1, and infinity. But then they're not functions anymore. They're we call them multi-valued functions. So you all know this. And you also all know what are multiple zeta values. So they're usually defined this way, but they are also the special values of these multiple polylogarithms with this particular kind of words at the point 1. Well, I mean, 1 is outside our domain, but it turns out that for this kind of words, which starts with some x0, then you can actually extend them to 1 without any problem. And they form a ring that I call Z, which is a very interesting ring, and many of you knows a lot about it. So I won't say much. Let me also mention that you can define the special values at 1 of any kind of multiple polylogarithms by some standard regularization procedure using the fact that they have at most logarithmic divergences at z equal 1. Good. And these regularized values are still multiple zeta values. Now, I want to consider the generating series of multiple polylogarithms because, well, you will see it's very important also in other talks to think in terms of generating series. So this is the unique holomorphic solution on U of this differential equation, which is usually called the KZ equation. I mean, you have to have some asymptotic condition at z equal 1 to get uniqueness. And in particular, the special value of this series is what is usually called the Drinfeld associator, which describes the monodromies of this differential equation. And there is a theorem of Francis Brown that you can have another solution of this equation, a real analytic solution, with this asymptotic behavior. And I'm not going to construct explicitly this solution, but it can be done explicitly, and it gives, I mean, it can be expanded as a series in all possible words, and the coefficients of this series are called single-valued multiple polylogarithms. So here I'm not being explicit at all because the purpose of this talk is not to talk about single-valued stuff, but there would be a lot to say about it. And let me at least mention that they are constructed as MZV linear combinations of products of the multi-valued polylogarithms. And well, they're called single-valued because, as I already maybe said here, this is a solution on P1C minus 0, 1 infinity. So in this domain, the classical multiple polylogs are multi-valued, but this is an actual function, so it's single-valued. And the simplest example is what happens with the x0. Well, with x0, you just get the sum of log z and its complex conjugate, so it's 2 times the real part, and of course, it's a single-valued. And it's very interesting, the fact that the map SV respects shuffle identities, which are all the algebraic identities in the algebra of multiple polylogarithms. So it's well defined on this algebra, and we call it the single valid projection. And it's related with some very deep stuff in cohomology, and maybe I'll mention something about it later. So now the special values of these single valued multiple polylogarithms are called the single valued multiple zeta values. And well, now this single valued projection that you had for the multiple polylogarithms, nobody tells us that it should still respect all the possible identities, algebraic identities between the special values, so between the multiple zeta values. But conjecturally it does, because we have many conjectures, very precise conjectures about the structure of the algebra Z of multiple polylogs, and also about the sub-algebra Z single-valued of single-valued multiple zeta values. So yeah, I mean, of course, by construction, these guys belong to Z, because as I said, they're Z linear combinations of these kind of products. But they span a much smaller ring, and for instance, it turns out that all the even simple zeta values just vanish, while the odd ones become twice themselves. Good. So now I'm ready to tell you something about string amplitudes. So I'm not going to be very precise about amplitudes because for lack of time and also of knowledge by myself, but the usual idea is to do a perturbative expansion in the string coupling constant, which is considered to be small. And in this expansion, well, it turns out to be a topological expansion because if you divide the strings between open and closed, and here I'm being very not precise because I'm considering actually only oriented strings in this talk. Then in one case, for closed strings, you get just an expansion on closed Riemann surfaces with an increasing number of holes. And in the open case, well, you have surfaces with boundaries. So this is, I know they look the same, but this is a disk with 4 points on the boundary, while this is a sphere. And then you have a cylinder, which is considered as a genus 1 object. What you count here is rather the Euler characteristic of the surfaces, but it belongs in the same group as the torus. And well, let's see what happens if you look at genus 0, which is by far the most studied and the most understood case. So you have, let's say you have n+3 string states on your surface, and then you have Mandelstam variables, Saj's, and permutations, rho and sigma. Then you can reduce essentially, I guess, all of the open string integrals to this set of integrals, which just depend on the two permutations, rho and sigma. So sigma exchanges the variables in the path from 0 to 1. So this is an iterated integral. And rho exchanges the variables in here, in the denominator. And let me also remark that you should think of this path as just a circle and the points on the circle that I've shown before. So this is the boundary of the circle. And the closed string building blocks, well, you have now the Riemann sphere, and rho and sigma, they both appear in the denominator for the holomorphic and anti-holomorphic variables. So it's very instructive to present the 4-point case because it has all the features, simplified features, let's say, of the general case. So you have the very first integral, 4-point case, so n equal 1. You have only identity possible as permutation. And well, this is well-known function, the Veneziano amplitude, which is expressed as a ratio of gamma function, and have this nice small alpha prime expansion, so for small values of the Mandelstam variables. And then there is the Virasoro-Shapiro amplitude for the closed string case. Again, this is a ratio of gamma functions, and it can be expanded for a small alpha prime. And you see in both cases, in the expansions, we start seeing multiple zeta values. So these are actually the simple zeta values, the Riemann ones. And there are two observations. So the first one, which is called KLT formula, is that you can express the closed Virasoro-Shapiro amplitude as a double copy of the open one. And the second is that there is a single valued projection between this object and this object. You just map in the expansion, term by term, the zeta values into their images. So the even ones disappear and the odd ones just get doubled. Okay, so now I'm ready to present the state of the art. So, well, I'm not going to be giving everything we know about it, just a couple of things I want to talk about today. So there are the KLT relations which generalize to any number of particles. Then the fact that in the open string integral Z, the coefficients belong to multiple zeta values generalize. This is, of course, a J. So the coefficients of the small alpha prime expansion of the J integrals, which are the closed string ones, are single valued multiple zeta values in general. And even more, this thing that I show you that you can pass from the alpha prime expansion of the open string integral to the alpha prime expansion of the closed string integral via this single valued projection is true for any n. And furthermore, there are recursive relation between open string building blocks, which originate from the KZ equation. And so you can get a lot of practical information. You can compute a lot of stuff, and there are many people. So here I've just cited some. I hope all of the people, well, probably some of the people who have contributed to these results, but then there are other things to say. And tomorrow, anyway, or some other day, Andrei Kaderli is going to talk about these kind of relations in genus 0 and genus 1. So you will hear more about it. Good. So now let's go to some mathematics. So I want to motivate the definition of elliptic polylogarithms. And to do that, we need to remind ourselves some basics about cohomology, first of all, and then about, let's say, about functions on the fundamental group. So this is going to be the next step. But let's start with cohomology and periods. So you take a manifold, then I hope everyone knows how to define the singular homology groups on the manifold. They're just topological objects, which are defined via this chain complex using the simplices. And this is a Q vector space. For instance, if you take Q coefficients, and you can take the dual of this vector space, and it turns out that it's equal. I mean, it's not a priori equal, but for Q it is equal to the cohomology, singular cohomology of the manifold M. And another group that you should know is the RAM cohomology group of the manifold, which is built out of the complex of smooth differential forms. So you have a derivation, and then you use this derivation to build these cohomology groups. Okay, and then by Stokes' theorem, if you take a class of a smooth form here, and the class of well, and the cycle sigma, then this integral is well defined. Why? Because this is a closed differential form, and so you can view elements of the RAM cohomology group as elements of the singular cohomology group, because the singular cohomology groups are just functions from the homology to well, to Q in this case. And I mean, I want to tensor with C probably here, because the RAM form will, I mean, this integral is going to be complex valued in general. But this is just a way to pass from one cohomology group to the other. And this was, it was demonstrated by the RAM that this gives an isomorphism between the two cohomology groups. So you see, you have to tensor with C here. Okay, and then there is an algebraic version of this story, which is not directly relevant in this talk, but it should always stay there, because all what I'm saying, some of what I'm saying can be made algebraic and should be made algebraic. So if you have an algebraic variety over Q, so you should think of a bunch of equations and the solution of the zero locus of these equations, then you can define something which is called the algebraic de RAM cohomology group of this algebraic variety. This is defined with hypercohomology, and I'm not going to give the definition. It's not very important, but for curves, there is a simpler way to define it, and I'm going to define it later, because we're interested in curves. And then Grothendieck proved the algebraic version of the de RAM theorem. So this algebraic cohomology is isomorphic to the singular cohomology. Okay, and the same thing hold for relative cohomology. So you can take out divisors from this variety, and you get periods in the sense of Kontsevich-Zagier. And periods are, I mean, So you can define them either as the entries of this matrix given the homology, or you can define them more elementary as integrals of rational functions with rational coefficients over the domains defined by inequalities, polynomial inequalities. Okay, and the RAM theorem for fundamental group is now the next step. So we have presented the RAM theorem for the homology groups. There is an analog for fundamental groups. So first of all, let me remind you that the first homology group of a manifold is isomorphic to the abelianization of the fundamental group of the manifold. And this can be seen, and it's convenient for us to see it, as the following quotient. So you take the group ring generated by the fundamental group over Q, and then you quotient by second power of the augmentation ideal, which is just the kernel, which takes any formal Q combination of elements in the fundamental group to their coefficients. I mean, you sum their coefficients. Okay, and I presented before the Durham theorem, and the Durham theorem tells you that you can describe all of the functionals on the homology group in terms of integrals of differential forms. Now we want to look for homotopy functionals, so functions on the fundamental group, or rather the group ring, Q by 1. And the idea again is to use integrals, but then if you do the exact same thing that you did before, you take a smooth one form, then it turns out that this is a homotopy functional. So homotopy functional means it defines a function on the fundamental group, so it just depends on the homotopy class of a path. And this is true if and only if omega is closed, and it turns out that then it can only detect elements which are in the abelianization of the fundamental group. But the fundamental group in general is not abelian, and so we are missing information on a lot of objects in the fundamental group. So it's just going to be 0 on that. And the solution given by Chen is to consider, instead of a simple line integral, iterated integrals of one forms. So you take smooth one forms, and then if this iterated integral is a homotopy function, so the iterated integral is defined iteratively exactly as I did in the definition of multiple polylogarithms, then it defines a function on this quotient of the fundamental group, and this is non-trivial function in general on any power which is less than r+1 of the augmentation ideal. So in general, with these iterated integrals, you detect more elements of the fundamental groups than what you would detect with just one integral. So of course you can take iterated integrals of length as long as you want. So r is the length of the integral, and so you can pass to the limit, projective limit of this quotient, and you get this, which is called the pro-unipotent completion of the fundamental group. You shouldn't be scared, just the limit of all these quotients. And then O is just the functions on this group. And then you quotient with C. And Chen proved that, I mean, I've already told you that any iterated integral gives you a function on this guy, but all of the functions on this guy come from iterated integrals, exactly as it happens with the cohomology. And so this is why this is called the Durham theorem from the fundamental group. And it was proven by Chen in the 70s, I think. And again, we're more interested in the relative version of this. So instead of considering loops and one base point, consider rather paths. So you have 2 points and paths between these 2 points. So this is the fundamental groupoid of the manifold. And well, how to compute all these homotopy invariant iterated integral in such a way that we can explicitly describe the pro-unipotent completion of the fundamental group. This is a not so easy question because you have a lot of one forms, a lot of differential one forms. You're not in the quotient, you're not in the cohomology, you're really looking at all the differential forms. And so the shortcut to do this is to use a model. I mean, because of course, if you take just random iterated integrals, they're not going to be homotopy invariant. And what is a model? So you identify a subcomplex of the complex of smooth differential forms, some subcomplex A, which is quasi-isomorphic to the complex of differential forms, which means that the cohomology of this complex, which is induced by the differential, is isomorphic to the cohomology of this complex for any n. And this complex, of course, I mean, this cohomology is by definition the Durham analytic cohomology of M. And the theory of Chen tells you that if you are in this situation, you can look at simply the homotopy invariant iterated integrals of the one forms belonging to A. And they give you all the functions on the pluripotent completion. And let me just show you what happens for P1C, which is the Riemann sphere. Well, this is well known. If you take this model, so here I'm writing this as a DGA algebra instead of as a complex, but it's equivalent. So you should think of this as the zero part of the complex, and this is the degree 1 of the complex. And well, these are just two differential forms plus the function 1. So this is incredibly easy, but it turns out that it describes the Durham cohomology of the Riemann sphere without 0, 1, infinity. And well, okay, but then it means that homotopy invariant iterated integrals of dz over z and dz over z minus 1, which are polylogarithms, multiple polylogarithms, describe all of the functions here. And we call them the periods of the fundamental group, base point 0, z. This is kind of, a priori, it's an abuse of terminology because with Chen's construction, nobody tells you that these guys will be actual periods for our definition, but it turns out that this rational model is algebraic enough to get us actual periods. Okay, so now I want to say something about compact Riemann surfaces, because we are going to focus on compact Riemann surfaces, and we know a lot more things on Riemann surfaces. And by the way, it's quite a special situation also because they're both algebraic curves and complex manifolds. So you take a genus G Riemann surface, you should think of them as donuts because I'm taking G bigger or equal than 1. And then you take these, I mean, you know that the fundamental group is constructed this way. And then the abelianization of this is just Q to the 2G. And well, I define an algebraic one forms of the Riemann surface. So this is an abuse of terminology actually, but I define them to be the meromorphic differentials on the Riemann surface. And then you probably know that there are first kind, second kind, and third kind meromorphic differentials on a Riemann surface. So first kind of the holomorphic ones, so those which span actually, which give the H10 of the Riemann surface. And then there are also second kind if they're meromorphic with no residues. So first kind is contained in second kind for me. And I define H1 the Durham algebraic of the Riemann surface to be the vector space of second kind differential quotient by the exact differentials, which are, I mean, D of some meromorphic function. M of x is the field of meromorphic function on the curve. So this is my definition, but it turns out it's a standard definition which came much before Grothendieck's definition of algebraic Durham cohomology when people were studying only curves, because this can be done completely algebraically, so you don't need to have the complex structure on the Riemann surface. You just take an algebraic curve and you do the same. And then there is the theorem of Grothendieck, which is true also with this algebraic Durham cohomology. And well, you still prove this by integration, but now this is well defined. Why? I mean, if you have singularities, you don't want your path to give you a different result if you pass on the left or on the right of the singularity, because then your integral wouldn't be homotopy invariant. But it's well known that you can avoid problems if your residue is 0. So by the residue theorem, if you take second kind differentials, you get a well-defined integration. And an algebraic, there exists an algebraic version of Chen's theorem for curves. This is very important. I think it was proven first by Richard Hayne. And that tells you that if you do this for iterated integrals, so there is a concept that you can define iterated integrals of the second kind, whatever this means. I mean, you just take second kind differential forms and then homotopy invariant integrals of these second kind differential forms. We call them iterated integrals of second kind. They have to be homotopy invariant. And then they're also describing all the functions on the pluripotent completion of the Riemann surface. This is another way of constructing the periods of pi1. And let me briefly mention that in general, in string theory, but I think in general also in mathematics, you're rather interested in configuration spaces of points on these Riemann surfaces. And this is my notation. So you have a Riemann surface, possibly punctured, and the configuration space of n points is just defined in this way. And well, the fundamental group, for instance, of these configuration spaces is well known and well studied in mathematics, related to the theory of great groups. And if you do the exact same game of that we have made with just one single Riemann sphere, with n points on the Riemann sphere, you get the multiple polylogs in several variables as periods of pi1. Okay, so yeah, let me briefly also mention that beyond genus 2, the description of the cohomology rings of these configuration spaces is not very explicit, so it's a priori hard to build models. And I told you that models are quite important if you want to construct all the periods of the fundamental groups. So this is probably the main difficulty in extending the theory of multiple polylogarithms beyond genus 1, let's say. But then let's take a look to genus 1. So this is the main part of my talk. So we want to look at a complex one-punctured torus. Why just tori and not general genus 1 Riemann surfaces? Because it turns out that all closed Riemann surfaces of genus 1 are complex tori. And well, one-punctured is just something that you naturally find in string theory, for instance. But it's also very natural from the viewpoint of considering the moduli space of these guys. So you take from now on tau in the upper half plane H, so the imaginary part is positive. And then you have a complex torus that I denote T, tau, which is just given by C quotiented by this lattice. So as I said, these are all the genus 1 Riemann surfaces, and then I want to take out the identity 0 of the torus, and I will denote the one punctured torus this way. Then you can, I mean, it's well known that the fundamental group is abelian for the torus, just Z2, and if you take out one point, it's not abelian anymore, so it's just free group on two generators, which are the cycles A and B, usually called. And well, of course, the first homology group is going to be equal to this in both cases, because you see the abelianization. And the second homology group, on the other hand, is going to be trivial in the case of one punctured torus, while it's not trivial for the full torus. And then you all know, I'm sure, the Weierstrass function and the Eisenstein series, but still let's give this definition. So this is the Eisenstein series of weight k It's a modular form of weight k, entering the definition of the Weierstrass function, which is defined, for instance, in this way, so as a in a neighborhood of the origin, as a meromorphic function with a double pole at the origin. And it turns out it's well known that the functions on the punctured, so the rational functions on the punctured torus, are just polynomials in the Weierstrass function and its derivative, with, of course, relations between the Weierstrass function and the derivatives. Good, so let's go to the RAM cohomology. So first of all, if you consider the algebraic RAM cohomology, well, it turns out, everyone probably knows that it can be described via the first, these two differential forms, dz and Weierstrass function times dz. So they correspond to dx over y and x dx over y if you think of an elliptic curve instead of the complex points of the elliptic curve. And well, it's also well known that, by the RAM theorem, you can integrate over the cycles, which in this case, the generators are the cycle A and the cycle B of the torus. And you get periods. Well, in principle, you would get periods if this construction I gave was algebraic. This is not quite algebraic, but it can be made algebraic. But let's say you get periods using these differential forms, which are 1 and 2, and quasi-periods using this other differential form, which turn out to be G2, the non-modular weight 2 Eisenstein series, and 2 pi I plus 2 G2. And the analytic RAM cohomology of these guys, well, is much simpler. It's just generated by dz and dz bar. Good. But we know that the analytic and the algebraic RAM cohomology must be isomorphic because they're both isomorphic to the singular cohomology. And one way to see this is, for instance, to identify the dz bar differential form to a combination of these two differential forms via this equation, which is, I guess, quite classical, and which allows you to, since this is just a total differential, so it's something that vanishes in the cohomology, and so you see that the class of dz can be expressed in terms of class dz and p of z dz. Good. So now we know a lot about complex tori, and we are ready to construct interesting stuff on tori. So let's talk about the Kronecker function, which was introduced in the 19th century and then found many applications in the last 30 years. So let me define zeta as this exponential and q as this exponential. And well, this is just quotient of the odd theta function with the eta function. So let's just define this function theta this way. And then you want to set, so this is the Kronecker function. You want to set this quotient of theta functions. So we will consider z as a point on the punctured torus, but alpha we will rather consider it as a formal variables. And of course, both these functions still depend on the modulus tau of the torus. So this is a multi-valued function on tau star. What does it mean multi-valued on tau star? It means that if you just continue it analytically along the cycles, spanning the generating the fundamental group, then it's not going to be invariant. And indeed, along the A cycle, so if you take z plus 1, it remains the same, but along the B cycle, so you take f of z plus 2, then it's going to give this monodromy. And furthermore, it has a simple pole at z equal 0 and no other poles on the torus. So we can formally expand this function f, and the coefficients of these expansions, called gn, traditionally in physics, are certain holomorphic, well, not holomorphic, meromorphic functions on the complex plane, which are not quite functions on the complex torus, because, as I said, this is a multi-valued generating series. And let's see what they are. So G0 is just 1. G1 is, well, it's just presented in this way, for instance. There's a simple pole at z equals 0, and then it has an expansion in terms of Eisenstein series. And it can be also written in terms of the, this is the Weierstrass zeta function, it's not the Riemann zeta function. And for a higher n, well, you get functions which are actually holomorphic at z equals 0. And they belong to this ring, so they're rational functions in here. So Weierstrass function and derivative of Weierstrass functions. And you add polynomials, I mean, you had powers of this G1 function that is in here. So a priori, it could have poles at z equals 0, but it turns out they don't. And the first definition of elliptic multiple polylogarithms, which we have already seen in Brito's talk, is this one. So you take these kernels and you consider an iterated integral. So at 0, in general, there will be problems, but you just regularize in the same way as always. And I want to stress here that z is in C. So I'm considering these as one forms defined on C, and these are iterated integrals on C, and they are homotopy invariant. So this is well defined because these guys are holomorphic outside the, they're meromorphic. And so why should we call these guys elliptic multiple polylogs? Well, this is kind of natural to do in string theory. Also, if you take the limit as tau goes to infinity, you get genus 0 multiple polylogarithms. So in general, you have an asymptotic expansion for tau going to infinity, and the coefficients will be just the genus 0 multiple polylogs, which is quite nice. And then I will give other motivations later. Anyway, this is probably the best working definition in string theory for sure, and possibly also in quantum field theory. The Brown-Levin approach now to define, to give an actual generalization of the multiple polylogarithms in genus 0 is to consider this correction of the form f. This is the Kronecker function from here. And then you want to multiply by this function, which is non-holomorphic. And then you get a well-defined function on the punctured torus, because it turns out that this 2 pi I times this guy has precisely the right monodromy when you go along the B cycle, because it gives a plus 2 pi I, but you can see here you got the monodromy a minus 2 pi I, and they cancel out. But it's real analytic, it's not meromorphic anymore. And a theorem of Brown-Levin is that, I mean, you can expand again. So this is a form now, not a function. I've added dz. So you can think of this as a generating function of one forms, omega n, and define also the one form 2 pi I d of im z over im tau. Well, you can construct, using these forms, a model for the RAM analytic cohomology. The RAM complex of the torus. So you just consider this in degree 0, 1, and then in degree 1 you consider you put inside your model all of these, so infinitely many forms. It's a lot of stuff. It's much worse than genus 0, but it's still much better than considering all of the possible one forms that you have on a punctured torus. And it turns out that this gives a model. And in particular, you take the first, I mean, this form and this form, omega 0, which turns out to be just dz, and they give a basis of the first cohomology group. So, I mean, to prove that it's a model, first of all, you should check that you get a 0-second cohomology group. And so you need that the wedge product of these forms, it's again the differential of some of these forms. And this turns out to be true. So, and you can do the same for a configuration space. And then a second definition of elliptic polylogarithms by Brown and Levin is that you take this form. Now I've added also this guy, and I'm doing something more formal than before. So I'm also adding into the business these two formal non-commutative variables. And this is now valued in the completion of this free Lie algebra on these two generators. Then it turns out that that this form, I mean, you can integrate it. You can do iterated integrals of the forms in here, and the coefficients of this very formal series here, which will be iterated integrals, special iterated integrals of these forms. It turns out that they generate all the periods of the pro-unipotent completion of the puncture terms. So this is the right mathematical definition in some sense of elliptic polylogarithms. But in fact, it turns out that you can in practice write these guys in terms of powers of the imaginary part of Z and the meromorphic functions introduced before. So this is one more motivation for calling these functions gamma tilde elliptic polylogs. Okay, there is another approach which I must start hurrying. So there is another approach by Levin and Racinet. They construct a different correction of the function f. So they multiply by this exponential. Okay, why? Because it turns out that you still get a well-defined function on the puncture terms. So you are defining a single-valued function because this function g1 has also the right monodromy along the B cycle to compensate for the monodromy of f. And why do we have two different ways? Well, recall I told you that you have this equation. And then this equation implies that if you take the class, so you take this dz pi or im tau on this side of the equation, then you take the class in cohomology. And then you have this identity in cohomology of differential forms. And well, it turns out that the periods of this guy and the periods of this guy then must be the same. And the B period, so the period of these two forms over the B cycle, which can also be thought as the monodromy of the primitives, are the same. And the primitives are nothing but, well, the completion of Brown-Levin on one side and the completion of Levin-Racinet on the other side. So it's not just two random functions that you take to complete your Kronecker function. It's just these two are quite special. And well, what do? You also expand this function that I called h, and the coefficients now are second kind differential forms. So we're now on the algebraic side of the story. And again, algebraic, I'm not really making it algebraic. I'm still considering Riemann surface rather than the algebraic curve. And by Ain's theorem, the periods of pi1, but then now I don't want to take 0 as one of the points, are all the homotopy invariant iterated integrals constructed with these second kind differential forms. So I've constructed in a different way the periods of the fundamental group, except for the fact that now, while these functions don't have a regular, don't have a simple pole at 0 anymore, they have horrible poles, and so you don't really want to put a 0 in here, and so you cannot really get the same kind of functions near the mark point. So there are ways. So this is just what I just told, I think. So you construct. I mean, you have to construct this connection formally in x0 and x1, and then the periods are the coefficients of this formal series. But there is a way around the fact that you don't have these simple poles at 0. This is a different story. There is an article by Ma Luo who constructed really algebraic version of elliptic polylogarithms, but he was forced, because he wanted a simple pole at 0, to add other poles in other points of the curve. Good. And let me briefly, very briefly mention that there are other approaches. So a classical one, which is just considering averages of the classical genus 0 multiple polylogs. And related to these, the ELI functions. And algebraic construction by some physicists who consider iterated integrals using integration kernels with at most simple poles. So they were not quite defined on the elliptic curve again, but they generate the same space of these guys. And they're also related to constructed all the primitives of rational functions on elliptic curves. And all this class of elliptic polylogs, which have their pros and their cons, are related. So, you can take special values of elliptic polylogs, but the way Enriquez defined them is a little bit different. So Enriquez defined elliptic multiple zeta values by considering the two cycles separately. So on the A cycle, you just consider the special value of the gamma tilde, and on the B cycle, you just consider the modular transform. And the upshot is that this definition was motivated by the fact that they're coefficients of an elliptic associator, so an analog of the Drinfeld associator, associated with a KZB connection, which is the analog of the KZ connection. But you will hear more about this in Kaderli's talk. And well, they're pretty nice functions related to multiple zeta values and iterated integrals of Eisenstein series. I'm not going to talk about this. I have to be very brief now. So genus 1 amplitudes have to do with elliptic polylogs. Why? Because you consider these kind of integrals over moduli space first and configuration spaces of points on the torus second, defined in terms of the Green's function on the torus. And if you only focus on the configuration space integrals, so you get rid of this integral and also of this function, which doesn't really matter for the mathematics, then you have that your closed string prototypes become these kind of iterated, well, this kind of multiple integrals, and the open string, this kind of multiple integrals. These integrals for closed strings are called modular graph functions, and they're very well known, and Eric Docker is going to talk about them tomorrow. And the open string integrals, where they are given by iterated integrals of functions which are very closely related to the kernels of the elliptic polylogs. And so what's the state of the art, very briefly? In genus 1, the coefficients of the open string integrals are elliptic MZVs, and the modular graph functions that I've mentioned in the closed string case are a very interesting class of functions, apparently related to the open string integrals by some single values like projection, and more concretely related to the elliptic MZVs, because they are combinations of holomorphic and anti-holomorphic elliptic MZVs. Moreover, there are also relations between genus 0 and genus 1, so this is a whole different subject, and this was proven in n = 2 or for open strings for any n. There are recursions also in genus 0, this will be in Kaderli's talk, and it's not known how to construct KLT relations, and there are partial results also for this modular space integration that I didn't talk about, and here there are names, but I'm sure this is not the whole list. And so in the -3 minutes that I have, I must say at least 2 words to conclude about beyond genus 1. So beyond genus 1, there are results in closed string theory. So there was a construction of higher genus analogs of modular graph functions, and they appear for sure for G = 2 and possibly for genus bigger than 2. We will learn something more with Eric Docker. And the hope expectations is that the nice things that we have seen at genus 0 and that seem to generalize at genus 1 should hold for any genus. This is what physicists seem to believe. So KLT relations, which are in some sense the same as single value projections because of twisted cohomology business that somebody else is going to talk about in this conference. And if somebody is interested, later I can, in the question time, I can say something about a possible strategy, which is a work in progress with Benjamin and Ricketts, on how to construct higher genus analogs of polylogarithms, which is something that people would imagine will show up in open string case for G equal bigger or equal than 2. So I leave the slide here and I stop, and I'll be happy to comment more about it. So thanks for your attention.
Thank you very much, Federico. Again, let's all take 2 seconds. We unmute ourselves, and then we give Federico a well-deserved round of applause.
Oh, yeah?
So I see that there's already a first question by David Waterst. David, please go ahead.
Thank you, Federico, for this overview. My question really arises first at genus 1, and in your maths background, you had a crucial slide that said shortcut, choose a model. Could you go back to that? Yeah, and so what I see at the bottom of that is a rational model for the projective line minus 3 points of iterated integrals of dx upon x and dx over 1 minus x, which I understand. But the puzzle I have is, to me, that is the model. Could there be some other model? And if so, how would it be related on the side of analysis? And I guess that question then continues non-trivially at higher genus.
Federico, you're muted. You're muted, Federico. You have to unmute yourself.
Do you hear me now?
Yes.
Sorry. So yes, you can construct different models in general, because I mean, you can even construct models which are related by related by chains of quasi-isomorphisms that are not directly related to each other's, and then about the fact that it's a rational model. So I wouldn't know. I wouldn't know, actually. I never thought about constructing a model yet in my life, but there's probably somebody else in the audience who can say something else. But in general, there are more models for the cohomology, I believe. But there are minimal models. This looks kind
you see,
minimal model to me.
Yeah, you see, I wanted to change that little word a, which you've chosen rather carefully, into the definite article the, and you're telling me that I can't because there's something that you don't know that could equally do the same job.
Yeah, so I believe, so I believe that this is the minimal model that you can choose, but in principle you can have more stuff which gives the same exact cohomology groups. So this is the best model for sure for P1C, I would say.
Thank you.
More questions? Yeah, Niels.
Hi, Federico. Thanks for a very beautiful overview talk. So just a remark, could we maybe go back to the very last slide of yours with the overview?
Sure. Here.
Yes, right. So just to add to this, because I don't think it's very well known and also not very well documented in the literature, But there's actually a third approach besides the real analytic approach of Brown and Levin and the meromorphic approach of Levin and Racine. So there's a third approach, which is purely algebraic and uses only forms of logarithmic poles, but you have to pass to a cover of the elliptic curve. And this cover is known as the universal vectorial extension of the elliptic curve. And so you're somehow changing the geometry a little bit. So you're passing to a cover of the elliptic curve, which is actually an affine bundle. So it's not a big change you're doing, but then this has the pleasant side effect that you can have your cake and eat it, so to speak. So you can work with, you can kind of work on the elliptic curve as it were P1 minus 3 points. And yeah, so this approach I think goes back to, as far as I know, to a letter that Deligne wrote some years ago to Dick Hayne and also to Ettinghoff and Enriquez. And yeah, but I don't think it's that well documented in the literature. So I believe Enriquez and Ettinghoff, they wrote a paper partially realizing Deligne's vision. And well, since you're working with Benjamin, you can surely ask him about this. You probably know which paper I mean. But just to say that there's a third approach, which is in some sense, well, which is purely algebraic. That is an advantage. And the shortcoming is that, well, you have to complicate the geometry somewhat.
Yeah. Thanks a lot. Yeah, I am aware of that. But I mean, for reasons of time and also for my personal ignorance on that approach, I wasn't thinking of including it. So thanks a lot for mentioning it.
You should really check it out, because another reason I think this will be interesting for Claude and collaborators and Johannes and these other people. It's very closely related actually to their approach, because what they are doing, kind of, if I recall correctly, is they work with a primitive of the P function, like a Weierstrass-Zeta function, and that's not exactly algebraic. I mean, this has a non-trivial transformation behavior, but if you pass to the universal vectorial extension, you can actually subtract this non-trivial transformation behavior, and you get actually that the Weierstrass-Zeta function gives you a well-defined differential form on the universal vectorial extension. So I believe that this is a way to make the considerations of Brittle, Dewar, and Tancredi and others purely algebraic in the strong sense. So yeah.
Yeah.
Just putting this out there.
No, thanks a lot. I will take a closer look. Thanks.
Okay. Well, thank you, Niels. And this is very interesting. If you want, and you have any kind of reference or just like hints of names of where one could find information, maybe you can put it on the chat.
I'll happily do that.
Then there's a question by Piotr. Or on Slack. Hi. I was just pointed out to me that one could also put it on Slack.
Actually, it's a question to both you, Federico, and Niels then. So this third approach, is that like analogous to, okay, it's a physics question. I didn't quite understand the math of this particular point. Is this is this universal cover related to having loop momentum in the, if you guys are familiar with that framework? Where you also have some sort of a universal cover because you cut your surface open, you cut it on the A cycle, and every time you cross this A cycle with the particle, it's like you're going on you're shifting some, like the value of your loop momentum by an integer unit. So you're kind of going on a cover of the surface. Is that, am I making sense to you? Or I guess I can just look at the reference that you will put on Slack or to make my mind, but I just wanted to ask you your opinion.
Yeah, what's certainly true is that there's some kind of universal cover of the elliptic curve in a algebraic sense. Yeah, I don't know what loop momenta, so maybe you know, Federico.
Okay, yeah. Okay, I'll ask you.
No, I wouldn't know too. Sorry.
Okay, thanks, guys.
Okay. Are there more questions? If not, then I think we can all thank Federico again. But before you leave, I think Matt wants to say a few words about what is going to happen tomorrow morning.
Yes, so we're going to be having a discussion session tomorrow morning as sort of a jumping off from the talks of today, there have been some approaches that have been very mathematical and geometric, and there have been some approaches that have been much more geared towards the particular details of how to solve a differential equation for particular integrals and hashing out efficiency concerns. So what we'd like is sort of a dialogue of seeing how the two different kinds of approaches can inform each other, how different people along that spectrum can give insights that the others can use. But anyway, just sort of as a jumping off point. So we welcome those of you who are interested. It's 11 a.m. Central European time tomorrow.
Okay. So if there's anything else you want to comment on, if you want to ask questions, have discussions, please feel free to use Slack. And also, I guess, feel free to hang out here if you want to discuss a bit more. And otherwise, I guess we see you all tomorrow morning, either at 11 for a discussion session or at 2 for the next series of talks, where tomorrow we will explore a bit more the relationship between elliptic polylogarithms, elliptic zeta values, and string theory. See you all tomorrow.